Okay, thank you for the introduction, and thanks to the organizers for inviting me. So this talk is based on some works from the last few years done in collaboration with Tobias Ekholm. Tobias is a mathematician, a symplectic geometer in Uppsala, and with Piotr Kucharski, who is now in Warsaw, and also about some upcoming work to appear very soon with Ekholm. And these projects grew out of our attempt to understand an observation relating knots and quivers, but eventually it ended up teaching us something new about how one can think about bound states of brains in M theory. So I thought this would be a fitting topic for the workshop. And my plan is to start by reviewing, well, what the knot-quiver correspondence is, so the motivations and the goals. And then I will explain how this can be understood from the viewpoint of M theory. And then in the third part of the talk, I will move on to some consequences. So some mechanisms that explains interactions of M2 brains mediated by M5 brains, which we call multi-Covers-Kane relations. And then finally, if time permits, I will talk a little bit about some of the new stuff in the paper to appear about how this whole structure lifts when instead of a single M5 brain, there's a stack of M5 brains. So the knot-quiver correspondence is based on an observation. So it's an empirical observation made by Kucharski, Reineck, Stosic, and Slutkowski in 2017. And what they observed is the following. So for example, take such a quiver like this one with 3 nodes and with arrows always going back and forth between nodes. So the adjacency matrix is symmetric. Diagonal elements are the loops on the nodes, and off diagonals count arrows in either direction. Then, given this quiver, one can study the representation theory. And in fact, for symmetric quivers with trivial potential, the representation theory was solved by Efimov. And the statement is that the partition function of Donaldson-Thomas invariants, so some mathematical objects that encode information about representation theory, actually takes a very simple and universal form where all the information about the quiver, namely the adjacency matrix, comes in this power of Q. Okay, so x1, 2, 3 are just some formal variables associated to the nodes. Then, given this structure, given this partition function, the claim is that if you take this partition function and you specialize variables, x1, 2, 3, to some powers of a, q, and x in this way, then what you get, after reorganizing it as a series in X, well, what you get is the generating series of Hopfli-Petit polynomials for a knot. In this case, it's the trefoil knot. And okay, if you're an expert, these are the reduced Hopfli-Petit polynomials. Okay, so that's an example of the knot-quiver correspondence. And more generally, this is not just a coincidence. In fact, it was observed that this holds for infinite families of knots. So for infinite families of knots, there is a quiver such that its partition function encoded by the adjacency matrix, Cij, upon specialization of the variables, given some integers, ai and qi for each of the nodes, then the generating series of the quiver specializes to a generating series of knot invariants for some knot. And well, remarkably, this is not only about Hopfli-Petit polynomials, it also extends to so-called refined knot invariants, such as superpolynomials. And one reason why I find this interesting is because at the mathematical level, knots and quivers have no relation in principle, but of course we know as physicists that they both come up in physics. So knots appear in Chern-Simons theory, and quivers oftentimes describe work volume dynamics of D-brane systems. So then one can ask many things about this correspondence from the viewpoint of physics. Well, first of all, is it possible to establish a relation between the quiver and the knot? What is the meaning of the nodes? What is the meaning of the arrows? And what is the meaning of the integers that define the specialization? And also, does this actually hold for any knot? Is it even a one-to-one correspondence? we're going to answer some of these questions. And then finally, whether it can teach us anything new about the physics that's related to knots and quivers. So there's a physics setup where this kind of generating series actually show up fairly naturally. I'm going to review this briefly. So given a knot in the three sphere, there is a canonical construction that associates to the knot another three manifold called the conormal Lagrangian. So basically you take the knot in S3, and then you take the tangent vector along the knot, and you take a plane in the cotangent of S3 of vectors or covectors that are orthogonal to the tangent. Okay, so that gives you a three manifold L in T star of S3, and L topologically is just S1 because it goes around the knot, and then at every point around S1, there's a plane, the conormal plane. So it's a solid torus, okay? But that solid torus in T star S3 intersects the zero section along the knot. And so what you can then do is you can consider topological strings, the A model on T star S3, where you consider n branes on the zero section. So the world volume theory is described by UN Chern-Simons at level kappa. And let's say we take a single brane on L. Okay, so there will be an abelian Chern-Simons theory living on L. Now, because these two branes intersect, there will be massless fields arising from bifundamental strings localized at the intersection. And these strings will give rise to matter fields that are charged both under the UN and under the U1. Okay, so they will be in the bifundamental. So that's the setup. And then what Oguri and Vafa did with this setup is they considered the partition function on S3. And what they argued is that it takes this form where this is the contribution from the bifundamental strings. And U here is a Wilson line of the UN theory on S3, and X is a Wilson line of the U1 theory on L. And then they computed this expectation value by reorganizing this as a power series in X. And what they argued is that the coefficients, after expanding in X, well, they coincide with traces of Wilson lines in S3. So in other words, this is capital U, where the trace is taken in all representations labeled by partitions with a single row. So in this case, it's symmetric partitions. And then according to Witten, these expectation values, therefore, are Helmholtz-Petit polynomials for the knot. Okay? So that's what comes out of this setup. And what's interesting then is to ask what happens in the large n limits. So we have n branes on S3. And if you take n to infinity, then it was argued by Gopakumar and Vafa that T star S3 gets deformed into the resolved conifold. So what happens is that the S3 shrinks to a point, the boundaries of open strings that give rise to the UN Chern-Simons theory shrink, and they become closed strings. And then it was checked by Gopakumar and Vafa that indeed the partition function of Chern-Simons agrees with the closed string partition function on the resolved conifold. So that's what happens if you just had branes on S3. If you have also a brane on LK, then the argument of Oguri-Vafa is that, first of all, this brane can be chosen to be special Lagrangian. So it has, remember, it's a solid torus. So it has a single deformation parameter that you can use to shift L off the zero section. So it does not intersect S3 anymore. Once you shift it off the zero section, the bifundamental strings, they stretch in an annulus from S3 to L. And then when you take n to infinity, S3 shrinks, and the annuli, they become just open curves with boundaries on L. So Oguri and Vafa conjectured that in the large n limit, the generating series of knot invariants actually must coincide with the open string partition function. But now, this is the open string partition function in the resolved conifold with an A brane on the knot conormal. So I'm just reviewing some fairly old story now, but if there's any questions, please. So through the sequence of dualities that goes back to Guri and Vafa, there is a precise relation between knot invariants on the one hand and open holomorphic curves, and observe that this kind of generating series of knot invariants is exactly of the type that appears in the knot quiver correspondence. So from this point of view, one should rather say that it's not a correspondence between knots and quivers, but really between quivers and open strings in the resolved conifold for not conormal branes. That's a slightly better way to qualify the correspondence. And so we start from here. And what we're going to do is we're going to start a genus 0, where things are fairly understandable in geometric terms. So a genus 0, the partition function, or rather the free energy, is dominated by disks. So that's called the disk potential. And a remark about the disk potential is that it is known that it is organized by some integral structure. Namely, this potential can be written as a sum over two integers I and j. J is the winding number of the disk boundary. I is the wrapping number over the P1 in the conifold. And then the basic object is a dilogarithm for the multi-coverings of a disk. And the coefficients turn out to be integers, also known as LM of E invariants. And the interpretation of this is, well, it comes from M theory, where these integers can be thought of as counting M2 branes with these winding numbers. So it's a reorganization of well-sheet instantons into dilogarithms that gets reinterpreted into M theory as M2 branes. Okay, so now since we're working at small string coupling, we can think of the brane as a geometric object. We can think of it as a special Lagrangian with a flat connection on top. In fact, it's an abelian flat connection because we have a single brane. And then the full free energy of the brane will include the disk instantons, but it will also be the classical action of the connection, which is the Chern-Simons action. So that action was computed in a very old paper by Elitzur, Moore, Schwimmer, and Seiberg. And it's just the logarithm of y times the logarithm of x, where x and y are the holonomies of the flat connection on the boundary torus. That's at the boundary of the Lagrangian. Okay, so if you do Chern-Simons on a solid torus, that's what the Chern-Simons action is at the classical level. Yes.
But that's some kind of string theory limit. But then you said something about branes.
Yes. Yes, that's right. Yeah, so yeah, how do they come in? I completely glossed over this point, but the point is, so at this point, I'm just doing topological strings, so a model in a Calabi L3-full. As I'm going to say a little bit later on, one can embed this setup into full-fledged string theory, right? That's natural. And then this would be type 2A, and I can lift it to M theory. So then the M2 branes would come from objects that wrap a holomorphic curve times the M theory circle. So there's a little bit of a chain of dualities. But this is just the open string version of what Gopakumar and Vafa did for the closed string.
Some future thing.
Some
the string expansion is some power series in the string.
Yes.
So if you're going to take an M theory limit, then you need to do some kind of resummation or orders in the string?
Right. So at this point, I'm only doing genus 0, right? So there will be higher corrections in G string later on, yes?
All right.
Yeah, okay. Yeah, okay, thanks. Thanks for the question. Right, so we're still in genus 0, right? We're doing some fairly classical and geometric reasoning. what I wanted to say is that there's not only the disk instantons, there's the classical action of the U1 connection, which is Chern-Simons action. And then if you minimize the free energy, well, then the critical locus is given by this equation. And if you take the exponential of this, actually it turns out that this can be written as a finite polynomial in variables x, y, and a. And this polynomial defines an algebraic curve in C star times C star that's argued by these authors to coincide with an object from knot theory called the augmentation curve. It's just a name, but the point is that this curve really comes from minimizing the free energy, and so it describes the vacuum moduli space, or if you wish, the stable configurations of the brane, if you only take genus 0 instantons. So this is what the augmentation curve could look like. It's a complex curve. Its points label configurations for L, which is a solid torus. And on L, we have the boundaries of holomorphic disk instantons. Now, on this curve, there will be some asymptotic regions where the disks are very large, so the instantons are suppressed. And on these regions, the connection, therefore, is flat. If you remove all the boundaries from the instantons, then the meridian holonomy Y becomes trivial. And the moduli space, therefore, is just the classical moduli space of the underlying Lagrangian. So there's a real direction R, and then there's a U1 flat connection S1. So the boundary regions must look like cylinders. In the interior, though, this picture is modified by the disk instantons. And so in general, this curve is not a cylinder, but it's a more complicated curve. OK, so I've only talked about the genus 0 picture so far, but let me formulate the proposal, and later we'll elaborate on this. So the proposal is that one can think of the quiver associated to the knot as describing the spectrum of genus 0 and 2 branes, which is generated by a finite set of basic disks. Okay, so there will be some basic curves that generate everybody else. So these are the LMOV invariants. And the geometric dictionary at this point in genus 0 is that the vertices of the quiver would be M2 branes on the basic disks. The arrows will correspond to linking numbers of the boundaries of those disks on L. And the integers AI will correspond to the wrapping numbers of the holomorphic disks, well, the basic ones, around the P1 of the conifold. There was another integer, the QI, but we're in genus 0, so we don't see that at this point. So that's the proposal. What I'm going to do next is I'm going to explain how this comes about, or provide evidence, and then I will explain how it generalizes to higher genus. So everything so far is very geometric. So we think of the brane and we think of disks, but this kind of notions really make sense or are well under control only at weak coupling. And so what we should do then is we should take the weak coupling limit of the Quiver partition function as well. So remember, the Quiver partition function is a sum over a bunch of positive integers, I, dj, one for each node of the Quiver. And it takes this form. So if we take GS to 0, and if we take a scaling limit where q to the di goes over to some continuous variable yi, then the sum becomes integrals, and the summand becomes the exponential 1 over gs. These denominators give you some classical dilogarithms of the yi. The Cij, di, dj go over to Cij log yi log yj, and then the formal variables, they give you log xj log yj. So that's the semi-classical limit of the Quiver partition function. But now the not Quiver correspondence claims that this is equal to some open string partition function whose leading order behavior is the disk potential. And so what we learned then is that the disk potential is nothing but a Legendre transform of this exponential here, which I call W tilde. So in fact, the disk potential in general can be organized as an infinite series of dilogarithms with integer coefficients. And so it counts generically infinitely many M2 branes. But what you see here is that this is manifestly just the finite sum of one dilogarithm for each node of the quiver. So the Legendre transform is the classical mechanism that describes how this interaction of a finite number of basic M2 branes generates the infinite number. Now, another consequence of the fact that W disk is related to W tilde by Legendre transform is that they must have the same critical locus, the same equations of motion. And so mathematically, what that means is that the critical locus of W disk, that was this algebraic curve, must be equivalent to a system of polynomial constraints which are derived by minimizing W tilde. So W tilde has a very simple form. It's very easy to write down what these polynomial constraints are. That's what they look like. And that's interesting because it's going to tell you something now about the basic disks. So first of all, if you have a brane with a single disk, okay, so the prototype of that is the toric brane in C3, then the disk potential in that case would be a single dilogarithm, and the moduli space of the brane would be described by 1 minus y minus x. Okay? Now, that's very similar to these polynomial constraints. So what does that mean? It means that we can think of this as having a number of basic disks, so one for each node of the quiver, and their boundaries will lie in L. Then these variables, xi and yi, should be thought of as the local holonomies around the boundary of the disk. So that's, in blue, is the boundary of the disk. Xi is the Wilson line, or the holonomy of the connection around that boundary, and the yi is the holonomy that links it. And then, well, you see here, the difference between this disk alone and the disk in a system with other disks is that there is some correction here, but that correction now is clear, because if one of the disks links another one, then its longitudinal holonomy x gets corrected by the meridian holonomy around another disks, and the power of that would be the linking number. Okay, so that's the argument that tells you that the adjacency matrix of the quiver is in fact the linking between disks in the brane. And as a check, if you do variable elimination on these polynomials, where you specialize the xi's as in the not quiver correspondence, and if you declare that the overall meridian at infinity is just the addition, or since we're talking exponentials, the multiplication of the little meridians, as it should, then you find that indeed variable elimination reproduces the augmentation curve as it should. So the picture is indeed consistent. So that's the genus 0 story. Now, what happens at higher genus is that it's a little bit harder now to think about this in terms of curves and classical objects. What's going on then is that at the level of the world volume theory, you have to deal with the quantization of Chern-Simons. And so what you have is that the path integral will define a state in the Hilbert space of the Chern-Simons theory. So we're doing Chern-Simons on a solid torus, so it's going to be the Hilbert space associated to the boundary torus. So that's one way to think about the open string wave function. It's going to be the wave function associated to this state in some choice of polarization. And the augmentation curve gets promoted to a Q difference constraint. So some operator that annihilates the partition function. Now, from the viewpoint of knot theory, Z open was a generating series of knot invariants. So actually, this constraint here describes a recursion relation for knot invariants. And well, these kind of recursion relations have been observed since a long time ago in a completely independent way. And that's how they show up in string theory. And if you go back to GS equal to 0 or nearly 0, then the WKB approximation reproduces the augmentation curve as the saddle point locus of this operator. Now, what happens at the level of the quiver? So now we take the full quiver partition function. We don't take any limit on that. And we would like to think of that as a wave function as well. And that's in fact natural based on what I told you, because now we have the brain, we have the boundaries of the basic disks, and around each boundary, what we can do is we can cut out a little neighborhood, like a little torus around each disk boundary. But then if you do that, you have Chern-Simons on a solid torus with many holes carved inside. So the Hilbert space will be bigger. You have a bigger Hilbert space, and you can think of then, well, the Chern-Simons path integral will define a state in this bigger Hilbert space. And the claim is that the quiver partition function is just the wave function representation of that state. Okay? Again, there's a choice of polarization where the position is given by the longitudinal holonomies, but that's the interpretation of the quiver partition function. And in fact, this wave function also obeys recursion relations like this one, which are nothing but quantizations of the polynomial constraints that we had before with appropriate powers of Q. And this is a fully general statement. So whenever you have a quiver, actually, it's always true that the partition function is annihilated by these equations. This is something that comes out very naturally if you think about quivers from the viewpoint of string theory. It's just Chern-Simons theory, really. Now, this is interesting, and it's going to be useful in a moment. Again, observe that the AI, now promoted to operators, they resemble closely the recursion relation for the single M2 brain, right? So this was the augmentation curve that we saw before for the single disk. But now it's an operator equation, and the wave function of that is well known. It's just the quantum dilogarithm. So the quantum dilogarithm counts, or rather gives you the multi-covering contributions for instantons deriving from a single M2. And now remember that in the full story, in place of x, we have some correction due to linking numbers. So with that in mind, let's define some new variables where we take xi, but then we shift xi by some correction due to the linking numbers, okay? So the claim is that if you introduce these variables, then it turns out that you can rewrite the quiver partition function in a very remarkable form. You can write it as the product of the contribution of single disks. There's finitely many, one for each node of the quiver. Now these are operator valued, right? They don't commute, these xi's. And then there's a normal ordering operation where basically you take all the y variables to the right. So the statement is that it's manifest now that the quiver partition function can be written as finitely many basic disks coupled together by linking. And this statement now is manifestly written in a way that holds at all genera. Yes, thank you. Yes, there is an ordering. And in fact, this is a bit of a subtle point. The ordering is actually arbitrary. So you can write this in many different ways. That's because, essentially, it's because the setup is topological. You can decide how you want to displace your disk boundaries. So yeah, it's a bit of a technical point. Maybe we can go over it in private. But yes, there is an ordering in the way that we define these variables, and that ordering will be reflected in the way that we write this. But there's not a single way of writing it because you can arrange things in different ways. So it boils down to who is closer to the boundary of the conormal. No, the result is invariant. Yeah, the result is always invariant. Yes. Yeah, thanks. Okay, so then we have finitely many basic disks. These variables are non-commuting, but somehow this must form all the bound states. It reproduces the full partition function. And so this must arise from interactions. And interactions will be encoded by the fact that these variables are non-commuting. There's a quantum holonomy algebra of these xi and yi's. And of course, the normal ordering operation also has an important role in this. And I'll come back to that in a moment. Very good. So what I told you so far is that the whole spectrum of M2 branes, or if you prefer disk instantons, is generated by interactions of finitely many disks. And on one side of the correspondence, we have the open string partition function, which according to LMOV can be factorized as an infinite product of quantum logarithms. These are classical variables with integer powers. The powers count the number of M2 branes, and this is the old genus multi-covering formula. And on the other side, you have this very compact way of writing the Quiver partition function with finitely many factors. And yeah, so the basic disks have integer power equal to 1. There's only one basic disk in each class. Now, the interactions, as we said, they must be encoded by this algebra of these variables, the fact that they don't commute. And in fact, we're doing quantum abelian Chern-Simons on L. Okay, so there's well-known U1-Skane relations for Wilson lines in Chern-Simons. And if we project these to homology, should have added a reference here. These were studied by Jakiv, Dunn, and Trugenberger in the late 80s. Well, then one can show that the Skane relations actually break up in this way. So the overcrossing is equivalent to Q times the splicing, and the undercrossing Q inverse times the splicing. And then if you have a curl, you can trade it for power of Q. Okay, so these are just equivalencies among Wilson lines in U1 Chern-Simons. And indeed, well, you can think of the quantum torus algebra of the variables that appear in this way of writing. Well, this algebra just reflects this property here, the fact that if you combine these two, then you get that the overcrossing, so y before x, is q squared x times y. Now, that's the algebra of Wilson lines, and then bound states are generated by the normal ordering operation here. And normal ordering basically means that you want to take these linked curves and you want to unlink them. Okay, so if they're linked, you have finitely many, but once you unlink them, you create new ones because of these relations. So again, you take your Skane relation, you write it as overcrossing is q squared undercrossing plus q splicing, and from one curve you got two. And if you keep unlinking all the way, then you generate the whole spectrum. So that's the basic mechanisms. Okay, and then there's this twist rule that you trade curls for powers of q. That's a minor one. Now, if you think about it, it's actually quite remarkable that this works out, because what I described is what happens at the level of the single variables. But in fact, somehow this structure preserves LMOV integrality. So we start from finitely many basic curves. We have these quantum logarithms. There is all sorts of powers of x and y inside. And I'm telling you that when you take this normal ordering and the dust settles, again, you can factorize into quantum logarithms in a consistent way. So from something that's organized into M2 branes, again, you get something that's still organized into M2 branes. That's not obvious at all. It's a property of the quantum dialog. We'll come back to that. But at this point, what this suggests is that the Skane relations on the single disk boundaries can be lifted from the single ones to the whole multiple covering. So there should be something like a Skane relation for the whole multi-covering contribution of the M2 brane. So let's believe this for a second. Then if that's true, the basic instance would be the following. You have two nodes corresponding to two basic M2 branes, or two disks, and they link once. Okay. And then, well, you apply the multi-covering Skane relation, and first you unlink them. So these are unlinked now. But then the price you have to pay is that you create a bound state. You do the splicing, and you get a third node. That's a new disk, and it has a self-linking. So I'll put a little curl on top. Okay. Now this picture represents something at the level of multi-covering. So these are nodes of the Quiver, so they're M2 branes. And indeed, if you write down the Quiver partition function for this system, then it's a double series on x1, x2. For this one, it's a triple series. But if you demand that x3, so the new node is just the bound state of x1, x2, then actually these two partition functions coincide. So these are Quivers with different numbers of nodes. that happen to have exactly the same partition function. And at this point, it's a prediction of the interpretation of Quiver nodes as M2 branes and the statement that you can apply skein relations to M2 branes themselves. In fact, this identity is a rewriting of an operator-valued equation known as the pentagon identity. That's an identity involving quantum dilogarithms with q-commuting arguments, x1, x2. And this identity is the basic mechanism that creates all bound states when you unlink M2 branes. And so it creates all bound states counted by LMOV invariants from the finite set of basic disks. And you can now take this identity or this basic unlinking procedure, and what you can do is you can start from an arbitrary quiver with linking k between two of the nodes, and you can either unlink them by 1 unit, so you get k minus 1. The price you have to pay is that the splicing will create a new bound state. The bound state will link with everybody else in a way that's dictated by the linkings of these two nodes with the others. Or you can add a unit of linking. Okay, so you can now say, just thinking geometrically, you can now say, if I have such a disk and it's linking with someone else, what happens if I unlink them? And then you can predict what the new quiver will be, and also what happens if you link nodes, okay? Just using skein relations, you can predict that there should be some equivalence relations among quivers with different numbers of nodes and different linking structure. And that's true. So one can show that this has the same partition function as that, and same here. And so an obvious consequence of this then is that the knot quiver correspondence, since it's only about the partition function, it cannot be one-to-one. However, every time you do such an operation, you end up introducing new nodes, because that's the splicing in the skein relation. And so what must be true, at least, is that there are minimal choices for the quiver. So there's always a minimal set of M2 branes that you can use to describe knot invariants. Okay, so what I've shown you is some equivalence relations among quivers. These were not known to mathematicians. They're just an immediate consequence of the physical picture, though. And I also told you that the basic relation was this pentagon identity. So I want to briefly remark on connection to wall crossing, which appeared in earlier talks today. So these kind of relations involving quantum torus variables and quantum dilogarithm identities are the bread and butter of the formalism of Kontsevich and Soibelman to describe wall crossing of BPS states. And in fact, the two setups are not entirely unrelated. In fact, in the work of Gayotom-Warnitsky, they consider wall crossing of BPS states in class S theories, and these can be engineered in M theory by wrapping M5 branes on a Riemann surface. And then the BPS states come from M2 branes that have boundary on that Riemann surface. So that's very close to our setup. We wrap the M5, well, I'm going to tell you in a moment, we wrap the M5 on a 3-manifold instead of a Riemann surface. But again, we count BPS states that arise from M2 branes, which interact through the M5 brane. However, it's not quite the same mechanism. Well, the setup is slightly different. And if you look closely at these multi-cover skein relations, then you realize that they're not quite equivalent to wall crossing identities. They're related, but not equivalent. And a simple way to see that is if you have two disks with two units of linking, then if you play the game of unlinking them or studying the whole spectrum of bound states, it's not quite what you would expect, for example, from the viewpoint of the gauge theory setups of GMN. So there is a relation, but it's more involved. And well, the way to understand that involves including domain walls in the Fordian equal 2 QFT and studying the interaction between domain walls and the BPS states. But that's just a side remark. I don't want to develop this too much. Now, there's a QFT side of this story. So now we come back to the lift to M theory. So what we can do is we can take the resolved conifold. It's a Calabi-Yau, so we can do M theory on the conifold times S1 times R4. And on the Lagrangian L, we can consider an M5 brane on L times S1 times R2. So by 3D correspondence, this engineers a three-dimensional theory with 4 supercharges denoted T of L. The spectrum of BPS vortices of that theory then is what descends from M2 branes wrapping the circle times a holomorphic curve. So the open string partition function then coincides with the vortex partition function of T of L. Okay? So that's the QFT setup that comes from lifting this to M theory. Now the catch is that for generic choice of 3 manifolds, it's not known what the theory T of L actually is, right? We don't have very good control on the geometry of these non-conormals, so we don't know what kind of gauge theory it is. We just know that it should exist. However, when the holomorphic curves on L are described by a quiver, a dual description of that theory is actually available. We call it T of Q. It's a dual description of T of L in the sense that it will have the same vortex partition function. And T of Q can be described very simply in terms of the quiver structure. So there's a U1 gauge group for each node. There's chiral fields, 1 for each node, and each chiral is only charged under the corresponding U1. It's neutral under the others. And the quiver matrix corresponds to Chern-Simons couplings among the different U1 factors, and the X variables encode phi A plus couplings for the various U1s. So the description is completely explicit, and given that, since it's a Lagrangian description, you can use it to compute the vortex partition function using results on localization on R2 times S1. And if you do that, you find that indeed the vortex partition function of that theory coincides exactly with the quiver partition function. So that checks out that this theory is what should describe the world volume dynamics of this M5 brane on L. Yeah, for this class of theories, yes. But again, this is a description, and it just reproduces the vortex partition function. I would not exclude that other descriptions would have higher rank gauge groups. However, notice that L is a solid torus, right? And you wrap a single brane on top. So if you just reduce the 2 form of the M5 brane, it seems that you would expect a description in terms of abelian gauge theory. Okay. Yeah, we're still doing a single brane. I don't know, but maybe I'll get to say something about the high rank later. Let's see. Okay, so now we had a duality among quivers. I told you that we can do linking and unlinking. We get many different quivers with the same partition function. Of course, that must relate to dualities among 3D n equal 2 quantum field theories now. Different quivers, you get different QFTs, T of Q prime, and the partition function is guaranteed to be the same. So the basic instance of that goes back to the pentagon relation, where you have U1 times U1 gauge theory related to U1 times U1 times U1. And actually, yes?
These are different theories, right? So the spectrum of operator
yeah,
is not the same. Right?
Yeah, well, we don't know, right? Yeah, I'm not sure, yeah. But yeah, the only statement is at the level of partition vortex partition functions, yes. So this is not, so if you just look in the literature, this is not the kind of duality that you immediately see for 3D n equal 2 theories, but in fact, if you just use particle vortex duality on these two, then you realize that actually the pentagon is nothing but SQED XYZ duality. And in general, we believe that the whole duality web on these theories T of Q should be generated by SQED XYZ. So then the answer to your question is that they're dual in this sense. Okay?
What is the dot? Pure the one with just a dot.
The one with just a dot, this one? No, sorry.
Yeah, I mean, the thing on the right hand.
This one. It's a U1 times U1 times U1, yes.
For two of them, there's no matter.
No, there is matter. So remember the description of T of Q is, yeah, this is, so the quiver doesn't describe the quiver gauge theory in the usual sense. So each node is a U1 gauge group, but it also carries a matter field charged under that gauge group. And the arrows, they're not matter fields, they're Chern-Simons couplings. Okay, so it's not the usual quiver description of gauge theories. It's a different description. Okay, very good. Yeah, okay, so now we get to the new and more fun part. So now what I'd like to do is I'd like to finally consider not a single brane on L, but a whole stack of arbitrarily many branes. So I'm going back to the A model. And I take MA branes. And okay, so then this setup was also considered by Gur and Vafa. And what they argue is that in this case, the open string partition function, well, it simply now computes Hopfli-Petit polynomials, or not invariants, in arbitrary representations labeled by partitions with up to m rows, okay? And then this is the Schur function in the open string moduli. So it's just that, again, you compute not invariants, but not only in symmetric representations, but in higher representations as well. Now, again, just like before, on the A brane, according to Witten, we have a Chern-Simons theory. And if we study this at finite string coupling, then this partition function here should be understood as a wave function representing a state in the Hilbert space of the Chern-Simons theory. Okay, so it should be just a wave function for that quantum state in some choice of polarization. And well, the Guri-Vafa setup tells you that you can think of this state as starting from the empty brane. So you just take the solid torus with UM Chern-Simons and no Wilson lines. And then you can create the state Z by acting with some operators. Trace lambda to the V inverse, well, these are just Wilson line operators. V would be the holonomy operator in the UM Chern-Simons theory. And it creates states with Wilson line inserted in representation lambda going around in the meridian. Okay, and then again, the coefficients would be these not invariants. Okay, it's just a way of thinking about the partition function. But then what we would like to do is we'd like to take both n and m to infinity, so both the branes on S3 and the branes on L. We take these to infinity. So taking infinite branes on S3 leads to the A model on the resolved conifold as before, right? Then we get that this quantum state is a sum over all partitions with no constraints now, because also m goes to infinity. And well, the state lambda, as I said, is just what you get from the empty brane, so just the solid torus, and you insert a Wilson line in representation lambda. So now we're summing over all partitions, and these operators that create these states satisfy an algebra. It's an algebra of Wilson lines in infinite rank Chern-Simons theory. And there's a boundary Hilbert space, okay? Now, the algebra of these operators, since these states are created from the vacuum by acting with the Wilson line, then it follows that you can compute the action of this algebra on this basis by taking a state lambda. So I'm taking an operator here that's a Wilson line in representation of rho. It wraps some ij cycle on the boundary torus, and I want to show how it acts on one of these boundary states. So I take my boundary state, I write it as the insertion of a Wilson line in representation lambda, and then I use the Skane relations to figure out what the product of the two Wilson lines is. So it's going to be some decomposition in new set of Wilson lines, and then when they act on the ground state, I get something that's encoded by these polynomials, which I can compute using the skein relations. So this is just to say that everything is quite computable, even though we are at infinite rank, and everything follows from the skein relations for the Wilson lines. Okay, so there's some cases which are especially simple. Just very briefly, if you have two parallel line operators, then their fusion is just what you would expect from the Littlewood-Richardson rule. So you take Wilson lines, parallel Wilson lines in two representations, you get a sum overall representations obtained by the fusion of rho and lambda, by the tensor product. And also observe that the way that we describe these bases for the boundary Hilbert space coincides with the definition of Verlinde basis. So the Verlinde basis in Chern-Simons theory is defined precisely like this. You take the solid torus and you insert a Wilson line going around the longitude in some representation, and that defines the state corresponding to that representation. We're doing this in infinite rank, but it's exactly the definition of the Verlinde basis. And what that means is that if you have an operator that wraps the meridian, then, well, it's a famous statement due to Verlinde is that it must act diagonally. So the S matrix diagonalizes the fusion rules. That's the statement here. And again, though, this eigenvalue of the meridian operator is entirely determined by the Honfley-Petit skein relations for the Wilson lines in L. So everything is determined by how Wilson lines behave. Now, in general, so these were simple examples, but in general, you will have, arbitrary types of Wilson lines. But okay, the point is that again, you can compute their algebra using the local skein relation. And if you have two parallel ones, you just use the Littlewood-Richardson fusion rules. And so because of that, all you need to know is how the Wilson lines in the fundamental representations act. You can get other ones by using the Littlewood-Richardson rules. And to do that, as I said, you can use the skein relations. So here they are. These are the skein relations now for infinite rank Chern-Simons on L, where AL is q to the m in the limit m goes to infinity. Okay. Now it turns out that this kind of problem has been considered by mathematicians. So Morton and Samuelson in 2014 wrote a paper characterizing the so-called skein module of the solid torus, which in physics means that they characterize the Hilbert space that we're after, and they tell you how the Wilson lines act on that Hilbert space. So we have everything we need. We can use it to compute. And okay, the description is somewhat involved, and you'll find it either in their paper or in our paper when it comes out, but it does give you complete control over the algebra of Wilson lines and over how they act on the boundary states. So what I'd like to do next, and this is the last thing I want to do today, is I would like to spend a few words about what happens to the recursion relation. So I told you that there were some Q-difference equations, A hat, that were characterizing the partition function. So before this was some Q-difference operator for the single brane, there was a quantum torus algebra. Now there will be some more involved operator. And what I'm going to explain is that these recursion relations, even in higher rank, they can be naturally understood in terms of this algebra of Wilson lines inserted at the boundary. So let's start with the abelian example. So back to the single brane that we discussed before. Remember, we had two operators, y hat and x hat. They Q commute in this way. And this Q commutator came, as I said, from the U1 skein relations, which take this simple form. Okay? Now, in that case, if we had for a single M2 brane, right, we said that the partition function was a quantum dilogarithm that you can write in this way. And in that case, the recursion relation was just 1 minus y minus x. And this can be understood as follows. So you have a bunch of curves in the interior. That's the partition function. At infinity, you act with, well, the identity operator. That's like an unknot, and the meridian operator, okay? And then you use your skein relation, namely the Q commutator. You push this through, and you rearrange your series, and what you get is that this is equivalent to acting on the torus at infinity with a Wilson line in the longitude. Okay, so that's how you get 1 minus y equals x, or at least how you can think about it in terms of curves placed at infinity on the solid torus. Now, going to full rank, the uplift of this simple example was worked out in the work of Eckelmann and Schende a couple of years ago. And what they showed is that the 1 minus y minus x gets uplifted to the unknot operator inserted at the boundary, the meridian, and the longitude multiplied by AL. And again, this is just a relation between three distinct line operators inserted on the boundary of the brane. So if we go back to AL equal Q, so M equals 1, then we recovered the recursion that I gave you on the previous slide. So what happens is that the sum over all partitions collapses to a sum over symmetric partitions, and then this operator collapses to 1 minus x minus y, okay? But in fact, this is much more powerful because you can do truncations for any finite value of m, and you can compute recursion relations in U2 Chern-Simons, U3, and so on, not just in the abelian one. So this holds for any value of m. Now, finally, the main result of the new upcoming paper is that we studied a link. So we took the Hopf link. So you can compute the partition function of colored Humphrey-Petit polynomials for the Hopf link using Chern-Simons theory. This was done by Witten. Or, okay, if you prefer, you can also express it in terms of the topological vertex. You take the resolved conifold with toric branes 1 and 2 onto external legs, and you can write down the partition function in this way using topological vertex. And what you find is that then this partition function should describe a state in the Hilbert space. Now we have two branes, so we actually have the tensor product of two Hilbert spaces for their boundaries. And that state is annihilated by some operators. Okay, and we give you the operators. They're fairly complicated, but the point is that, well, this can be done for any framing, but then you can do some checks. For example, if you throw away one of the branes, okay, then this reduces to the unknot recursion for the unknot, for the other brane. And again, you can specialize to the abelian case, and you recover the quantum augmentation curve for the Hopf that was worked out some time ago. So in the abelian case, it matches with what we know. But now the main point is that the way that we derive these is not combinatorial. That would be way too difficult. So the partition function is quite involved. And you would have a really hard time guessing these kind of relations. And so the point is that one can derive these geometrically. So you take your solid tori, and there's a framework in mathematics called knot contact homology. It was worked out by these people roughly 10 years ago that tells you how to compute the curves that you need to insert at infinity. Anyways, the point is that this can be done systematically for other knots and links, and so you should be able to compute these kind of recursions for all rank partition functions in other cases as well. Right, way out of time, so I think I'll just leave my conclusions here and I'll stop here.